Okay, this is the second of two supplemental discussions on LabVIEW VIs that will be used for the calibration in the force and displacement lab for ME-144L. In the first supplemental discussion, I reviewed this simple VI that modeled the output from the bridge output, and the reason we wanted to use that was as a model for the output voltage that will in the lab actually come from, of course, an actual measurement. So the point is to automate the steps in the calibration process. So let me show you a VI that we're going to use for this purpose. And it's a lot here on the front panel, so I'm going to sort of direct you to a couple of things first. All right, so this VI, let me show you the block diagram. So the block diagram has this while loop, and within that while loop is what's called a case structure, right? So this case structure. Okay, I'm not going to show you how to build this, but I am going to post a link to a very good online tutorial that shows how to build this particular type of LabVIEW program, which is a finite state machine. And a finite state machine is a type of program model, if you like, that's used quite a bit in designing many types of programs and actually systems, and it's used for embedded system design, for example. So it's a really useful tool. And so the finite state machine model in LabVIEW, you can find a lot of information about these online, has the while loop. So as soon as you start running this, it enters into this while loop and begins running this case structure, and it wants to know which case to run. And the way you start it is usually with some initialization. So you see this, the state that's indicated here, it first starts off with an initialization, so you can tell it where to start. It starts off on the initialize. So in a case structure, you can click here and look at the different states. Since you're learning about states in dynamic systems and controls, this is different from a state like a state of a physical energetic system where the states are variables like displacement and so on. This is a state of the system, of the program. It's a mode of operation, if you like. So every time it enters this state, this is the initialized state, and the state machine is a program model. It runs the code in this case, and so each case has code within it that you can specify. After it runs, we have wired into it here, and these are constants that can be chosen that are based on the states, right? So there's another state. After it initializes, it says read the data continuously. So it's going to tell this state machine where to go. Now I'll show you in a second where that comes from. Okay, but it knows what state to go to next based either on you telling it where to go in the next process or making a decision based on inputs that you might specify here. Okay, I'm not going to go into that. Refer you to that really nice, and it's actually a short tutorial on state machine design in LabVIEW, and I'll put a link on that on the course log if you're interested. So what I've done then is created this state machine, and you can put in these states, and these states I chose in the following way. So let's think about what this calibration process would require. What do we want? You're going to start off you're going to say, I'm going to measure so many data points, or maybe you don't know how many data points, which is why it's nice for this program to be adaptive to you if you're going to have a program running and automating the data process. But you want to initialize, then you want to begin reading data. You want to be able to make the decision, is that good data? If it is, you want to store it. And after you store it, you then want to reload the beam in a different way, take more data, store it, or maybe you don't like it. I won't go into make the program too complicated because you could add a lot of steps, but we want to read the data, we want to tell it, save the data. And after you've taken all your data, you want all that displayed on the screen. You want to be able to look at it and make sure that you're done And then you want to be able to tell it, okay, model that, give me the calibration, or save that, and also save that data if you like. You can add the save part. I haven't added it on this one. So the way you can do that, and it's very intuitive, that that you want to initialize. So you have an initialize, an init state, and you can draw this out, and it's helpful this way. You can then say, okay, after I initialize, I want to read data, right? So and so this is a state, and then you want a transition, and this transition occurs through some action that you're going to define. So there's not going to be any action. The init state can only go right into the first state that you want it to go to, and then you can specify this. Remember, you're using this, so you can say start reading, read data. And here's where you can put your DAC, and you're constantly reading that data, right? Now, in here, you want to have different transitions, right? You want to be able to tell the program, I want to save that. So I want to have another state over here that says save, and maybe update the display, right? That's what I did. Update the display. So that's, we're going to define. So in order for this is going to be running continuously, taking data. When you decide, you're going to tell it, hey, record that. And that's what you would do if you were doing this by hand, right? You would say, I like that data, I'm going to record it. You tell it to record, save that display, and then what do you want to do? Well, you want to go and take more data. You want to update your load on your beam, for example. So what do? Well, it automatically should go back here. Once it's done saving and updating, you could tell it not to transition out of here unless you told it to, but we're going to say go automatically into here. So comes in, saves it, updates it, then goes back, starts reading more data. And then here you could again tell it, oh, I updated it, save, record my data. So here's the calibration process that you're automating, right? It's a nice little machine. So once at some point here, you're going to say, I've collected all my data. It's all been displayed. It looks good. Then you're going to have maybe another state. And that state is the one that's going to say, hey, model that for me. And it's good and quit. So I'm going to make it simple. Now you could tell it here, model and quit, and then here, you could tell it to stop. Or you could say model it. Maybe you don't like the way it looks. If it doesn't look good, then you might say go back and read some more data and change the data. So again, I'm gonna keep it simple. So nice, simple little program guide. Maybe you've seen something like this before in different ways, but this is the way you can at least begin designing your. So you can see your program. So you can see the states are the init, the read data, continuously save, and model and quit, and then there's a stop state, which means the program to stop. So there's 4, and that's why, going back to my little VI here, when I created the states, you can see initialize, add to my arrays, and save it, update the plots, model and quit, and then here's the read continuously. They're maybe not in the order that I'm going. It doesn't matter because they can jump around, right? And each of these states again has the transition decision. So here, as soon as it finishes this, it reads continuously. I'll show you the read continuously next. So once it reads continuously after it initializes, look, this should be familiar to you if you went through the first part of this supplemental discussion. This is the model of the beam. In here, I've put that beam model, gives me the output voltage. So you see, it's simulating. Oh, I applied a force, so there's that force value. Here's the output from my data acquisition, and oh, it's the ith step because I'm being very careful about how I record my data. And so this is running continuously. Right, you're in this case, and it's a while loop. It's going to keep running and running until you tell it to stop. And here's the stop. Now the stop occurs for 2 different conditions. One, if you tell it either to record the data or to build the model and quit, just the way we just discussed, right? So those are the 2 transitions. If you tell it to record the data, then it's going to stop. Or if you tell it to build a model, it's going to stop. So for either case, that's an OR, right? And those ORs are found under the right under the Boolean VIs. But in the case where you build the model and quit, note that the logic comes out here, and here's where the transition decision is made. It says, okay, if, and what is this? This is called a selector, and this says, if this is true that you told me to model and quit, then choose the model and quit, and so it sends out the state to do the model and quit. So it goes into that state. If you didn't tell it to model and quit, then it goes to add it to the array and plot. And so let's look at that state. So if I'm going to go add to the array and plot, what it does is it enters this state, right? And all it does here is it takes the measured, and I'm using, these are going to look new, but these are the results of local variables, okay? So these hopefully have been introduced in a previous tutorial. But all it's doing is it's I know this is replacing a part of the array. You're telling it what part of this array of the output voltages to replace with this I. So you can go back, for example, and tell it, hey, on the second index, I want to replace that with the value I just measured. So it's going to have a fixed number of array elements that you can replace here, right? So it's either replace array subset. You're telling it which index to put that value in within that array, and then it's storing it in the voltage output, in the force data that you're specifying, right? Your calibration data, and it's plotting it for you. Now, you could add another choice. So instead of saying, actually, I'm saying, fill in the array. Let's say you wanted to make the array bigger. Actually, the first time I did this, I used a insert array instead of using. So here's the replace. Let me do it over here because it's outside of the. So you see the insert array VI. What that'll do is it'll add an element, so you can build, even though so you can tell it to make the array bigger if you like. So you can have another state that says, you know what, I want to insert a point between two different points. I don't want to replace a point. I want to add a point. So you can make this program more complicated if you like. All this is doing is filling up a set number of arrays, array elements. Okay. Also, this is only got force voltage data. You could add here more code. For example, if you collect data for, say, the force, you also are inputting displacement data, for example, for the tip deflection. So here's where you would add that, and you would build up that array. Okay, so I think we've looked at all of the states. Initializes all the arrays to 0. Add array, we just saw that, and it updates the graph. Read continuously. Here's where, in the lab, you would want to put a little DAC assist in here, or some data acquisition or something else here that collects your data, right? And then finally, when you tell it to model and quit, here's the final state. You bring in the voltage and the force data that you've collected from your calibration, and you put it into a VI here. I lost my context help. There you go. The linear fit data. And so you see, you send it under Y, the force, right? In this case, because you want force versus voltage. So you have Y and X. X is going to be the voltage. So you see I put force in the Y, voltage in the X. Tell it I want a least square fit, right? Here you can go to the help and get more information on that linear fit. And then what it sends out is your slope and intercept coefficients for that least square fit. And then it also sends out, for those input voltages, given that linear model with these coefficients, here's what the model would predict. So it gives you your model output. Okay, the reason you don't have to always output that, but if you want to compare for a given voltage, this is what your model is going to give you, is that model. You want to know how good that correlates with measurements, right? You want to compare it. So that's what I'm doing here. Now I'm actually putting on a different graph And you could probably graph this on the same original graph. I didn't stop to figure out how to do that. I think it's just got to think yourself through it. I think you could also go ahead and plot it on that original graph and make your VI front panel a little bit more concise, or use tabs maybe and create a tab where you can flip over now and show the results of the model. However you want to do it. I'll show it to you. I'm going to double click on it because I scrolled out of it, but you can see what I'm creating is two XY graphs. Note when you're building an XY graph this way, right? If you just send two arrays into this bundle, it creates this cluster for a single plot. If you first come, if you want to create an XY graph with multiple plots, so in this case I want one plot, right, of the original force voltage data, and then one plot of the model force with the voltage data. I want to put those together. So first you bundle them, create these two clusters, and then you use a build array, put those together, and then plot it on your XY graph. Right? There's plenty of help for how to do this. Sometimes I remember how to do it. Sometimes I have to work my way through it just by hands-on. So this shows your force sensor calibration. If you have your deflection data, you add a similar linear fit if you like. If your model is linear, like for your beam, and if you plotted the force measured, right, input, versus the deflection of your beam, here's where you could have a linear fit for force versus displacement of the beam, and that linear model coefficient, right, would give you the stiffness that we're looking for the beam, right? So then you could add that code in here and output that. So to find this, to show you this graph, there it is, right? So that's the data originally captured versus the model. I didn't run this, so let me run it and show you how it works, and I'll show you the steps, and now you know everything that's behind it. So you can tell it how many data points you want. This may change. If you want to make an adaptive number of steps, you might have to make some changes. This displays what state you're in. You can't change anything here. This is set by the program, by the inputs that you specify. Again, I know that finite state machines are maybe a new concept to many of you, so hopefully I've explained enough here so that you can go back and understand how to use the basic structure. Again, go to that online tutorial. It's brief, maybe 10 minutes, and it really explains finite state machine design very well. Give it the index value for the values that you want to enter. Remember, LabVIEW starts off with an index value of 0 on its arrays. You should constrain these so that you could constrain it to start at 1 if you wanted. I started at 0, so then you put your applied force and start everything off at 0, 0. Then you can tell it, okay, hey, run, record that data point. I want the first one. So here are the steps. I put them down here. Program starts on initialize. Remember, it starts initial. By the way, if you're going to modify this in the lab to include displacement data, you could add inputs here. So because you're going to put the applied calibration force here, if you're inputting displacement data from a sensor, from the laser sensor, for example, you're not measuring that with the DAC, then you might have to input the data here to get the deflection data. All that data is then displayed. Here are the arrays. The force data that you input, this is your input forces, and you're going to have calibrated masses for that and forces. And then here's what's measured from the model, right? But you would have a DAC system that would give you these volts. And then if you had more voltages, let's say from the LVDT or from your measurement, you could put those output here so you could see them. And then finally, here's from the model, the output. So this is from the previous run. But let me show you. I'm starting off 5 points. Index value 0, 0. Program starts an initialize and begins reading data, but not recorded until told to. So you set the index value and the value of the applied force. Again, add other inputs, change those as you read them. Again, remember, you're automating that calibration process, and this thing's running for you automatically and doing your modeling. Now, when ready to record, you click record that data. Right? Then it's going to repeat. It's going to go back and start reading more data. And you just keep, you can, hey, I didn't like that data point, redo it, or change the index value, go to the next one. Remember to change your index values, or just going to keep rewriting on that same index value. Again, you could improve this program maybe if you wanted. You can go back to any point and set the index value. Let's say we finished. Hey, I want to go back and change number 2. Just enter 2 and rerun it. Once you see the data looks really good, when complete, press the build model and it's going to quit. Again, this is just a simple example to show you how you can automate the calibration process, trying to make this a little bit more interesting and not just doing some dry by hand calibration collection. So let me run this guy. It's running. It's got a 0, 0. Remember, 0 the data on initialize. Got 0, 0 here. Everything. Don't want to build a model here. It'll give me an error. So you might actually tell it not to do so if you haven't run. Again, I don't want to make the program, but here 0, 0. Record that point. Index 1. Let's say I apply again 1 Newton. Record that point. Now look, I've got a 0 point here, a 1 point here with some voltage that it has measured. Right? Where did that voltage come from? It came from my model. And if I scroll up, actually, you'll see that model is the same model that is in part 1 of this supplemental discussion. Is up here too. I just hit it. Now I recorded that. Index value 2, force 2. Now I have 3 points. Index value 3, force of 3. Record. Now I have 4 points. Collect my 5th point, or index value 4. Value 4, and now I've got all my 5 points. I like my data. I now want to run a calibration, so what do? I hit build model and quit. And it finishes, and down here, scroll down, and there's your data versus model, right? And your coefficients are there. Again, this is ending here, but you could, as I mentioned, have the state come back and say, hey, there's your model. Are you done, or do you want to keep running? Again, just another opportunity for you to learn a little bit more LabVIEW. The whole concept of finite state machine is very useful for a lot of different applications, for controls, for building robots, and so on. And that's how we've used it for other applications. I hope this has been useful. Again, I'm going to post this on the course log. Also post a link to that tutorial that I like so much. And if you're interested, you might take a look at that. All right. Thanks.